All right, guys, just take 5 more minutes just to relax and then we'll get back into it.
Okay, hello everyone, I'm Wahid. I'll be taking you through the next half of the Year 11 Physics module, and I'll be going through Mod 3 and Mod 4 of Waves and Thermodynamics and Electricity and Magnetism. Oh, there is a lot to cover, so I'll just get straight into it. And if you guys have any questions, just post it in the chat. Okay, so Waves and Thermodynamics. So these are some terms and definitions that are really important to the module. So these just describe the different types of waves that there are. So a transverse wave is one in which the energy is transferred perpendicular to the direction in which the particles of the waves moves. So what does this mean? So a transverse wave is basically like a sine or a cos wave. The direction in which a transverse wave moves, say it's in the horizontal direction, the x direction, like this. And the way which these particles actually oscillate is perpendicular to the direction of energy transfer. So what that means is that energy or the particles are being oscillated in this direction, and the wave itself is transferring energy horizontally. Remember, an important thing to note is that the particles themselves aren't actually moving. It's just that they are transferring energy. So for the longitudinal wave example, what's happening is that in the transverse wave, the energy is being transferred 90 degrees. In a longitudinal wave, it's being transferred parallel. So what does this mean? If we have a particle like this, these particles are bumping into each other and transferring energy this way. So what I meant by that the particles themselves aren't moving is that these particles are just vibrating onto each other, so colliding onto each other. So this particle collides onto this one, and it transfers energy onto the next one, and onto the next one, onto the next one. And once they're done colliding, or once they've done transferring the energy, they move back to the original rest position. So an example of a longitudinal wave will be a sound wave. In sound waves, what we have is compressions and refractions. So if in our sound wave, the air particles basically vibrate onto each other like this. So they're vibrating onto each other, and then they go back to the original positions like this. But we'll go into this more in detail in the later few slides. So these transverse and longitudinal waves are the different types of waves. So you have a transverse and a longitudinal wave. The different forms of waves, however, are mechanical and non-mechanical waves. So what this means, what a mechanical wave means essentially is that it needs a medium to travel through. So a sound wave would be a good example of a mechanical wave. Without air, sound cannot be propagated, right? Because it requires the air particles to move the energy across the space. Without air, so if, for example, in a space, there can be no sound because there's no air. A non-mechanical wave, on the other hand, is just a wave that doesn't require a medium. So the only example of this is electromagnetic radiation. What electromagnetic radiation is basically light. So radio waves, microwaves, visible light, gamma rays, all that stuff. So those are non-mechanical waves. It's a pretty simple distinction between the two, but it's a really important definition. Okay, and this is some wave diagrams to help. So this over here would be a longitudinal wave. Longitudinal, and this is a transverse wave. So the difference, as we discussed earlier, is that a longitudinal wave, the direction of oscillation is parallel, remember, parallel to the direction of energy transfer. So it's oscillating this way, and the energy is also traveling in this way. However, for a transverse wave, it's quite the opposite. The energy transfer is this way, so it's propagating that way, but the particles themselves are oscillating up and down like this. Okay. Some important notes for these waves are the different types of, what can we call it, properties. So in a transverse wave, how to actually identify it or gather information from it is we use these points. So amplitude, cycle, trough. So crest would be the peak of the wave, where the wave peaks, how much energy is at the maximum point in the wave. A trough would be the lowest point in the wave. The wavelength would be how many waves occur in, or how, sorry, we'll go into the cycle. So a cycle is how many waves, how long does it take for one wave to occur? And the wavelength is the distance quantity of that. So you can think of cycle and wavelength as kind of the same thing, but cycle in this sense would be time, and wavelength in this sense would be the distance. Okay, and the amplitude is the distance from the equilibrium position. So the equilibrium position is this line here, the resting point, to the maximum point. So the maximum point being here, and maximum point being there. So the magnitude of a maximum, where does it go to the lowest point and where does it go to the highest point? And if we correspond that to the longitudinal wave, if we line them up, the wavelength for a longitudinal wave would be the distance between each compression, so from here to there. Okay, so we'll go into some equations to describe the properties of these waves. So the most important parts here is probably this one and this one. The last formula isn't as important, but it's just good to know. You will definitely see the second formula every year, V equals F lambda, describing the relationship between velocity, frequency, and lambda, and the wavelength. And the first one is also really important, the frequency, 1 over period. So the frequency is describing how many cycles occur per second. And this wave number is describing how many wavelengths occur per meter. That's the distinction. But the real important two are this one and that one. You don't really need to know the third one. Okay, so we'll look into those questions later, some example questions later. Now we'll just go into the behaviors of waves. So for year 11 physics, there's 3 distinct properties of or behaviors of waves, being reflection, refraction, and diffraction. So reflection, as it's said, is pretty intuitive, is when the wave reflects. But what we need to know is how it reflects. So if you have a plane surface like this, the way a wave will reflect is that the angle of incidence. So the angle of incidence is the angle from the normal. So we'll draw a bigger diagram actually up here. So if this is our normal, if that's our normal, and this is our wave, the angle of incidence, the angle at which this wave hits the surface is this one. So this is our theta I, our angle of incidence. This angle in the law of reflection will be the same as the angle of reflection. Okay, so that's the law of reflection. It just states that the angle of incidence, the angle at which this wave hits, is the same as the angle of reflection. And don't get confused. When you're given these types of questions, make sure it's always measured from the normal. It's never measured from this surface here. This is wrong. Okay, it's always measured from the normal. Okay. Refraction is basically when a wave changes its direction when it enters another medium. Okay, this medium has to be of a different optical density. So just imagine it as something more dense, a more dense material. Then this wave will refract. And again, like the reflection case, this will refract based on the normal. Okay, so what we're measuring the angle from is this normal angle over here. Okay, so the angle of incidence in this case, so theta I and theta R are described by a different property called Snell's law, but we'll look into that in a different case. All you need to know is that refraction means when a wave changes direction when it enters another medium. Okay, and diffraction is another behavior of a wave, not as important in year 11, but it will be a lot of help if you know it right now, because in year 12 you'll see it. Diffraction is when a wave bends or changes direction when it passes through an opening. So for example, if you have an opening like this, a small gap, and you have a wave, it's a really bad drawing of a wave, but what happens is that this wave will change direction. So as you can see, it's being more curved out. You see why this happens in year 12, but for now, just understand that it happens. It's really complicated, the reason why it happens, but you'll get to it eventually. Just know that it happens. So if we look into some examples, this is a pretty simple example. It asks us to find the frequency of the wave. So we know from the relationships before that velocity is equal to frequency times the wavelength. So if we write down our formula over here, we can just simply sub everything in. So we know that the velocity is 65 and the frequency is what we're trying to find out. So it's unknown times 0.8, which is our wavelength. If you plug that into your calculator, you should get 81.25 hertz. Okay, and the units for frequency, remember, is hertz. So what hertz means is amount of how long it takes for the wave to complete how many periods or how many cycles occur in 1 second. So this is essentially just 1 over 1 second. Okay, but if that's a bit confusing to you, just know that the units for frequency is hertz. Okay, so we'll go into another example. Rufin is standing in shallow water and notices that over a period of 24 seconds, 15 waves crash into him. Okay, so this is a bit more complicated. So when we get a complicated question like this, it's best to draw a diagram. So we'll just draw a diagram to make our lives easier. So it says that in 24 seconds, 24 seconds, t equals 24, 15 waves crash into him. So what's happening is 15 cycles of this one wave. So 15 occurrences of that wave is occurring. Okay, so we have to just draw that 15 times. Obviously, I'm not going to draw it 15 times. So I'll draw a dot, 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 and then it continues up here. Okay, so what we need to find is how long it takes for one cycle to occur. For one cycle to occur, it's simply just the total time divided by the amount of waves that actually occur. Okay, and this will give us the period of the wave. So how long it takes for one cycle to occur. Okay, and this will be 24 over 15 seconds. Okay, and it says the distance between two adjacent crests in the wave is 1.5 meters. Okay, so we'll write that down. Lambda equals 1.5 meters. What is the velocity of these waves? Okay, so we know from a previous example, velocity equals f lambda. All right, but we don't have f here. But we know that the relationship between the frequency and the period is given by frequency equals 1 over t. So we simply just sub in our period and we get 15 over 24 hertz. Okay, and now plugging it all into our formula of v equals f lambda, we get 15 over 24 times 1.5. Okay, and you should get 24 times 1.5. 0.9375 meters per second. Okay, so that wasn't as complicated, but it's just a matter of drawing a diagram and trying to interpret what's happening in the question. Okay, so sound waves. So this is discussing further into sound waves. So as we saw before previously, sound waves are a longitudinal wave. So they're vibrating parallel to the direction in which the energy is being transferred. And the places where the particles are being compressed are called compressions, okay? Compressions. And the places where they're being expanded upon in the sound wave are called rarefactions. Rarefactions and compressions. Compressions, just think about it as being squished together, and rarefactions as being stretched out from one another, okay? And the points of compression would be where the particles are gathered most, so in this region around here. And the points of rarefactions will be the point where the particles aren't as compressed or close together. So in this region over here, like that. Okay. So sound waves, the amplitude of a sound wave is directly related to its loudness or volume. So that's pretty intuitive. However loud the sound wave is will describe its amplitude. And for the frequency of a sound wave, it's dependent on the pitch. So if the pitch is really low, that means the frequency is really low. If the pitch is really high, that means the frequency is really high. Those are some intuitive definitions. Okay, so what these two formulas describe is the intensity. So what the intensity means is how much, or the rate of change at which kinetic energy of air particles, so how much air particles are passing through a point of area in a certain distance. Okay, that's what intensity means. So it says that these formulas relate to sound waves, but in reality, they relate to all waves. So the intensity of any wave can be described by these formulas. Okay, so this first formula describes if you have some power. So for example, I have a speaker and I know that it produces a power of 10 watts. You can determine the intensity of the sound at some distance r. Okay, so how much that sound actually diminished over some distance. And what this second formula describes is the intensity at one point compared to another point. So if you knew from the origin point over here, so if you have the origin point in yellow, and another point over here. So if you knew the intensity at some distance r over here, then you could also determine the intensity at any other distance r. This is what that formula is describing, but we'll go into examples right about now. Okay. So first example, an observer standing 4 meters away from a sound source records hearing the sound at an intensity of 9 watts per meter squared. Yeah, so this is the units for intensity, watts per meter squared. Okay, so how many watts are there per meter squared? So how much the sound actually diminished over that distance. So we'll draw a diagram as usual. 4 meters away from the sound source, records a hearing the sound at intensity of 19 watts per meter squared. Watts per meter squared. Okay, determine the intensity of the sound 9 meters away from the source. Okay, so 9 meters away, something like this. It's a pretty awful diagram, but we'll do. So we're trying to find the intensity at that point. Okay, so we know from the formula that I1 R1 squared equals I2 R2 squared. All right, so for the first case, we already know both the intensity and the distance. So we can plug that into I1. So if you plug in the intensity of 19 and plug in the distance of 4. Okay, and for the second case, where it's 9 meters away, we don't know the intensity. So we're just going to leave that as I. Okay, but we do know the distance of 9 squared. Okay, and simply rearrange 19 times 4 squared over 9 squared. Okay, you plug this into your calculator, you should get 3.75 watts per meter squared. Okay, and one important note is to always leave your answers in decimals. Okay, never leave your answer as a fraction. Okay, always leave it as a decimal. So we'll go into example 2. Gladys is standing at a concert, at the front of a concert near the speakers. She moves away from the speakers such that she is twice as far from the speakers relative to her previous position. Okay, so if this is a speaker, and Gladys is originally standing at some distance up. We don't really care about what distance she's standing at initially. We just care about that she's standing at a distance up. And then she moves away twice as far. So then after that, she moves over here twice as far. So 2r. This total distance will then be 2r. 2r, okay? The intensity of the sound she will hear at this distance is A, B, C, or D, okay? So what we have to relate to this question is that we know that the speakers in both scenarios output the same amount of power, right? Because the speakers themselves aren't changing. So we write down here, the power of the speakers is just P, okay? Now, what formula for intensity relates to power and radius? If we go back here, it's the first formula. Intensity equals power over 4 pi r squared, okay? So for the first case, the intensity 1, what we have is I1 equals power over 4 pi r squared, all right? So that's just the simplest form you can write it, because the radius is r and the power is p, okay? But for the second case, the intensity 2, so this is I2 at a distance of 2r, the power is still the same, remember, but the distance in this case will be 2r. So instead of writing r over here, like we did in the previous case, we're going to write 2r. All right. Now this, if you simplify it, will just give us 16 pi r squared. And now what we're asked to find is the intensity of the sound she will hear at this distance is something times the previous intensity. Okay. So if you factor out a 1/4 in this new intensity, what do we get? Okay, and something to notice here is that this expression is the same thing as I1. So what we're now going to do is just sub in our I1, 1/4 I1, right? And this gives us a relationship between the second intensity and the first intensity. So I2 is equal to 1/4 times I1, okay? So if we know that I2 is the intensity when she moves away, we just look at each of these cases. So A, 2 times the previous intensity, no. Half times the previous intensity, no. 4 times the previous intensity, so 4 times. We do have the 4, but that's 4 times. It's becoming less, so C wouldn't be right either. D, 1/4 times the previous intensity. Yeah, since it's being diminished by 1/4 as she's moving distance, it will be D, okay? So 1/4 the previous intensity. Okay, all good with that? Yeah. So now we're going to move on to the Doppler effect. So what the Doppler effect basically states is that the observed frequency of a wave, it doesn't have to be a sound wave, it can be any wave, will decrease or increase depending on the relative motion of the source, okay? So the source being the thing that's actually creating the wave. So why this happens is, if we look into this ambient example, this stationary object is moving towards this guy over here. As it's moving towards him, each of these waves are being, think of it as they're being squished upon one another, right? So they're becoming closer and closer and closer to one another, all right? And since each of the waves are becoming closer and closer to one another, the frequency is therefore what? It's increasing, right? Since this wavelength, right, the distance between each of the cycles is decreasing, the frequency must increase, right? Because remember, velocity equals f lambda. So as this lambda is decreasing, this frequency must increase if this velocity is the same, okay? So it's just describing how the frequency will change as there is a relative motion between some sound or some source of a wave and an observer, okay? And the way this formula is described is this one, okay? We're using this formula. And I'll show you how to apply this in the next step. It's really important to remember this formula, but if you can't remember it, it's not, don't worry, it's all on the reference sheet, okay? It's a bit complicated, so we'll go through this next example. So I'll write down the formula just so we don't forget. So this apparent frequency equals to V plus VO over V plus VS F. Okay. So an observer is traveling in a car at 60 kilometers per hour. So again, we're going to draw an example just to make our lives easier. 60 kilometers per hour. And here's a car home from a car traveling in the opposite lane of 100 kilometers per hour. Okay, this is traveling at 100 kilometers per hour. And it's producing some car horn. All right. So the frequency of this wave, this natural frequency of this wave is, so FO is equal to 1,500 hertz. Okay. And we know that the velocity of a sound wave is 340 meters per second. So we're just writing all our information down, and then we're going to properly try and interpret the question. What frequency of sound would be noted by the observer? So basically what we're trying to find is the observed frequency from this observer over here, from this guy, from the car traveling at 60 kilometers per hour. Okay. And an important thing to do in these types of questions is to assign a direction. All right. So this car is traveling to the right, and this other car traveling at 100 kilometers is traveling to the left. So what we're going to do before we even start the question is assign a direction. This is really important because it will depend, or it will vary our signs over here. So these signs will change, this plus and minus, these two pluses can change to either a minus or a plus depending on the direction we assign. So since we're starting or we're counting the origin point or measuring our sound from this observer here, we're going to let right be positive. Okay. Let right be positive. All right. So if right is positive, then any motion towards the left will be negative. All right. So we're going to be plugging our values in, but we have to be really careful here because we notice that there's two different units. There's a kilometers per hour and a meters per second. So we need to convert everything to a meters per second because that's the SI units. It's easier if we convert it and leave our answer in SI units. So to convert 60 kilometers per hour to meters per second, we can just simply divide by 3.6. Okay, that's just a simple conversion that you really need to know because it comes in handy. And to convert from meters per second to kilometers per hour, you just multiply by, or you multiply by 3.6, the other way around. All right. So 60 kilometers per hour divided by 3.6, that gives us 50 over 3 for the observer. And remember the velocity of the wave. So this V over here is the velocity of the wave is 340. All right. So velocity of the wave is 340 and the velocity of the observer is 50 over 3. Okay. Over the velocity of the wave again is still the same. It doesn't change. It's 340. But in this case, we know that any motion towards the left is negative. And this car over here, let's say the opposite car horning, is traveling in the direction of the negative. So instead of writing a plus here, we're going to be writing a negative since it's traveling in the opposite direction to which we assign as positive. So what it will be is 250 over 9 meters per second, but it will be negative. So 250 over 9 meters per second negative. Okay, so I just converted kilometers per hour to meters per second. And FO is 1,500. So we'll just plug that in there. Okay, and this will give us our final calculation. If you plug all this into your calculator, you should get the final answer. I'm not going to do it because it's a really long process to plug it into your calculator, but this will be your answer. You just plug that into your calculator. Okay, everyone good with that? Okay, so put a dot there. Okay, standing waves. So standing waves are another form of wave that are formed from superimposition. So what superimposition is the interference between at least two waves. When two waves combine or intersect with one another, all their components, so all the ordinates at any point will add up together and it will form some different sort of wave. It can look like anything, it can look like really crazy, but all you have to know is that superimposition is the interference of two waves where you add up each of the ordinates at the point. And how a standing wave is formed is when a wave is traveling, it hits some type of surface and it bounces back. And when it bounces back, that second reflected wave will interfere with the original wave. And those will interfere in such a way that it forms a standing wave. And what a standing wave will look like is something like this. So it oscillates back and forth in this similar motion. So it's oscillating down, and will look something like that, oscillating back up, it will look at the top one, okay? And you need a certain type of frequency to form a standing wave. So you can't just do at any frequency. You need a discrete frequency to form a standing wave, okay? And we'll look into more of that later, okay? So harmonics, it doesn't really go, so I'll just go through it now. So standing waves, what we have to know is that the first harmonic, the first standing wave formed is called the first harmonic. And what it has is it has one antinode. So if you move this wave, so imagine you have a rope and you're shaking the rope. If you shake that rope at a certain frequency, what's going to form is a standing wave, right? If you connect that rope to a wall and shake it at a certain frequency, you're going to form the first harmonic. You're going to form a wave that looks like this. If you continue shaking it increase the frequency, what's going to happen at some point, the wave is going to look something like this, right? It's going to form two antinodes like that, okay? And it can keep on going, but you will need more and more energy to make those standing waves, okay? Harmonics. So what harmonics tells us, it gives us a formula for calculating the frequency of a standing wave, but I really don't like using the formula. I'd rather just derive it on my own. So you can know the formula if you're running short on time in the exams, but just note that using a formula is not as good because you don't get a good grasp of the actual concept itself. So we'll do the questions without the formula, but we'll first analyze what it means. So for a string fixed at one end or a pipe closed at one end, so what this means is if you have one end over here and it's an open end over here and you're shaking this rope, a standing wave, sorry, this is a really bad example. So we'll just do with a pipe example. If you have a pipe like this, it's opened at one end, right? So a standing wave formed looks something like this. Okay? I really can't draw. Okay, and one thing to note is when it's at the open end, it's always going to form an antinode over here. And when it's at the closed end, it's going to form a node over there. So the antinode being the point at which the wave reaches its amplitude, the maximum point, and the node being the point at which it's at its resting position, okay? We'll look into questions later if that's a bit confusing right now. And for strings first, closed at both ends, so something like this, nodes will form at both ends and the antinode will form in the middle, in the center like that, okay? So the nodes being the point at which it's at rest and the antinodes being the points at which it's at the maximum amplitude, all right? So we'll go through this example. An unfingered guitar string is 0.7 meters long. So we draw a diagram, 0.7 meters long, all right? And it's played at 330 hertz, all right? So it says that it's formed at the first harmonic. So the first harmonic means that it forms one antinode only, all right? So one antinode like this. That's the first harmonic. If it says second harmonic, then it would be two antinodes. So something like this, all right? So just remember that the harmonic corresponds to the amount of antinodes there are. What is the speed of the wave on the string, okay? So we're trying to find the velocity of this wave. So length being that. So to find the velocity of this wave, what we know from the previous equations is that velocity equals f lambda, all right? We already have frequency as 330 hertz, but what we don't have is the wavelength. To find this wavelength, what we need to do is analyze this situation. So in this example, when it's the first harmonic, it's of length 0.7 meters. So this wave here is only half a wave. If you look at it, if you're trying to continue this on, what a full wave will look like is something like this, right? Because remember, a wave is just one cycle. It goes to the top, to the bottom, and back to the start. This, what we have in the first harmonic, is only this section over here. This boxed section there, right? What we want for the wavelength is that entire section. So to find the length of a full wavelength, what we have to do is multiply this length by 2. So this wavelength will be 0.7 multiplied by 2. And that will give us 1.4 meters, right? So the velocity then would be 330 times our wavelength of 1.4. And that will give us 462 meters, right? So it was just a matter of seeing how many full wavelengths there are. We noticed that this isn't a full wavelength, that this portion there isn't a full wavelength. So we extended that a little bit further, and then we calculated the length of that full wave, all right? So we can also use the formula, but as I just did, I didn't use the formula. I analyzed the question. I saw what was going on, and then I applied the formula or derived it myself, right? So it's better not to use the formula. But if you're really struggling, then just use the formula, okay? So we won't have time for example 2. We'll go into the refractive index. So the refractive index just relates to the refraction of a material. So how much or how slow is the wave when entering a material going to travel depending on the refractive index. That's all this formula is saying. So how fast will the wave travel when it enters the new medium of this refractive index? This is what this formula is describing. It's a pretty simple, and it's just a ratio between the speed of light and the velocity of the wave in that new medium, right? So this is a pretty simple formula. The more important formula is Snell's law, and this allows us to make the calculations or to see the angle formed. And it states if you know the two refractive indexes and one of the angles, then you can determine the angle of refraction. And one important thing to note is that, say if this medium over here, so the highlighted one is of less density or less optical density than this one over here. So it's entering a medium of higher density, all right? What's going to happen is that the wave is going to refract towards the normal. So when it enters a medium of higher refractive index, is going to refract towards the normal, all right? But when a wave is entering from a more dense to a less dense, it's going to bend away from the normal. Okay, so less to more is going to bend towards the normal. More to less is going to bend away from the normal. All right, so these are really important things to know. Total internal reflection. So what this means is that when a wave is going from a more dense medium to a less dense medium, say that this is air, so the refractive indexes of air is 1, and this is water. This is water. So when this wave is traveling through this water, at some angle, what's going to happen? If you keep increasing this angle of incidence, if you keep increasing it, at one point, it's going to bounce back, right? It's going to bounce back and reflect inside the medium. This is what total internal reflection is. The reason this happens is because as you increase the angle of incidence, the angle of refraction will keep on increasing also. And as this angle theta I increases, this theta R will reach some point at which it's 90 degrees. And any more than that will reflect internally. That's when total internal reflection occurs. And the formula or to find the angle of incidence at which total internal reflection occurs is described by sine theta I equals 1 over n. Okay, pretty simple formula. And this is all given on your reference sheet. So you don't really have to memorize these, but it's good to memorize these. Okay, we'll go through this example here. So we'll just go through A, try B yourselves because we have a lot of slides to cover. We'll go through A. Light traveling through an optical fiber, n equals 1.44, reaches the end of the fiber and exits into air. So always draw a diagram. No matter how simple the question is, just draw a diagram. It will save a ton of time because if you get confused, you can always refer back to the diagram. Okay, so n equals 1.44. 1.44 reaches the end of the fiber and exits into air. Okay, one thing you have to assume is that the angle of, or the refractive index of air is 1. Okay, this is just something you have to consider. Okay, now, if you look at this question, recall from the formula that n1 sine theta I equals n2 sine theta R. So we'll just write this down so we don't have to worry about it. I equals n2 sine theta R, all right? If the angle of incidence on the end of the fiber is 30 degrees, what is the angle of refraction? Refraction outside the fiber, right? So this angle of incidence and angle of refraction always measured from the normal. Remember, it's always measured from the normal. So what we're going to draw here is this as 30 degrees. And what we're trying to find is this angle here, this theta R, all right? Simply subbing everything into your formula, we know that n1 is 1.44, since it's the incident surface, and theta I is 30. So sine 30 equals n2. We know that n2 is 1, it's entering the new medium. And what we're trying to find is the angle of refraction as theta R. So then sine theta R would be equal to, or theta R would be equal to sine inverse or all this 1.44 multiplied by sine theta or sine 30. All right, and plugging this into your calculator, you should get 1.44 times sine 30, 46 degrees. Okay. So have a go with part B. We don't really have that much time to go through all of them because we have a lot to cover. But have a go with part B after we're done with this. Okay, thermodynamics. So this is the next part. So we finished all of the waves. Now we're on to thermodynamics. So thermodynamics is just the study of matter and how matter interacts with other matter. Okay, so all matter is made up of very small particles. So you and I are all made up of atoms, and all these atoms are vibrating at some amount. Right? They're all vibrating because they have some amount of energy. And as you give the atoms more and more energy, they will vibrate more vigorously, okay? And this kinetic theory, so this is basically called kinetic theory, how the study of how atoms vibrate. This kinetic theory applies to all types of matter, so solids, liquids, and gases. So if you heat up a liquid, the particles in a liquid, even though they're separated much more than solids, they'll vibrate more vigorously until they reach a point where they turn into a gas. So at that point, all the particles will break apart and float free in space, okay? So that's what this sixth dot point is saying. The distance between particles in a gas are large compared with the size of the particles. Yeah, so they're separating really far away. Okay, energy and temperature. So these are some important points. You really don't need to know this third dot point, this second dot point. The really important one is this first one. So the average kinetic energy of a system is related to its temperature. So whenever someone says temperature of this object, really what they're referring to is the average kinetic energy. So all these particles, they all have some kinetic energy since they're vibrating, and that for the entire system, the average kinetic energy is related to its temperature, okay? So Celsius and Kelvin. So Kelvin is another way to measure the temperature. All Kelvin is a different offset to Celsius. The reason they have this is so they don't have to go to negative values. The lowest possible Kelvin is 0 Kelvin. And what this is negative 273 degrees Celsius. So what that means is that absolute zero or 0 Kelvin is a point at which particles stop moving. So now, if you have an object, all the atoms in that object at absolute zero will stop vibrating. So they will have a 0 energy, okay? And if you go higher and higher, obviously they'll get more and more energy. And the way to calculate or convert between Celsius and Kelvin is just to add negative 273 to a Celsius measurement. So negative 200, so 0 degrees Celsius is 273 Kelvin. So to convert from Celsius to Kelvin, you add 273.15. From Kelvin to Celsius, subtract 273.15. It's a really simple conversion. All right. So we'll go into the 0th law of thermodynamics. So what this says is that when two objects are in thermal contact, so when two objects are touching one another, they will always reach the same temperature. So there will be no energy or energy transfer between the two objects. So the objects will reach the same temperature. So if I touch an ice cube, my heat from my hand will melt the ice cube. And if you let some amount of time pass, the water melted on my hand will be the same temperature of my hand. That's what the 0th law of thermodynamics is describing. That when you have two objects in thermal contact, they'll always reach the same temperature given some amount of time, okay? And the first law of thermodynamics is really just the law of conservation of energy. What this says is that an energy can't be created nor destroyed, only added to another system or transferred, okay? So this is what the first dot point is saying. States that the energy simply changes from one form to another. So heat energy going into kinetic energy, going into potential energy. That's what the first law of thermodynamics states, okay? And this formula just says the change in internal energy, so how much energy this system gains is equal to the amount of heat added to the system and amount of work done on the system. So if I'm running, if a heater is blowing onto me and I'm also running, the heater is the heat added to the system and the work done is by me running. So that's the total change in energy in my body as I'm running, okay? So we won't go through that one. It's a pretty simple example. All you do in this one is add these two values together, but that's for you to do at home. We'll go through changing temperature. So this formula just describes the change in energy given a change in temperature of a certain object. It's a very simple formula to remember. Just remember Q equals MCAT, right? This is a cat, right? CAT and MCAT. It's a really easy way to remember this one. Q equals MCAT. And this just says the amount of heat or heat transferred to a certain system given a temperature change, okay? Specific heat capacity. This is a constant for certain values and describes how much energy is needed to increase the temperature of a system by 1 Kelvin. Okay, this is just a constant for any material, and it will always be given to you in the question. Okay, I think the specific heat capacity for water is given in the formula sheet, so you won't be given that, but for any other values like steel, you'll be given the specific heat capacity. Okay, so let's do this question. So a hot water tank contains 135 liters of water. Initially, the water is at 20 degrees. Okay, so we'll write down all our information. First, we write down the formula, Q equals MCAT. Okay, Q equals MCAT. And we know that the mass of the water is 135. So 135 liters is the same thing as 135 kilos. All right. Initially, so at T equals 0, so T0, the water is 20 degrees Celsius. All right. Calculate the amount of energy that must be transferred to the water to raise the temperature to 70 degrees Celsius. Okay. So T final, the final temperature being 70 degrees Celsius. Okay. So in this question, they don't give us a specific heat capacity, but if you look into the reference sheet, the specific heat capacity of water is 4.18 times 10 to the power of 3. You don't really have to write the units down because it's really complicated. So just write down the actual value of it. Okay. So we're subbing everything in. Now the mass is 135. The specific heat capacity is 4.18 times 10 to the power of 3. And the change in temperature, so the change being the final minus the initial. Final 70 minus 20, that gives us 50. And if you plug this into your calculator, times 4.18 times 10 to the power of 3 times 50 will give us a really large number. So it will give us 28215,000 joules. Okay, but just remember to convert this to scientific notation. All right, I'm not converting it now because I'm just being lazy, but remember to always convert it to scientific notation. Okay, thermal equilibrium. So this is the same thing as the zeroth law. All it's saying is that when two objects are in the same system, so when they're in thermal contact, they'll eventually reach the same temperature. So when you put ice into water, the ice will heat up and that therefore melt, and the water will cool and until they reach some same temperature, and they'll keep that temperature unless more heat is added to the system. Okay, and what it says is, as such, the sum of all change in energy of objects in thermal equilibrium will be 0. So what's happening is that this ice is being heated, right? So its change in energy, its change in Q will be greater than 0, right? It's because heat is being added to the ice because the water is warmer than the ice, right? But since for the water is being cooled by the ice, right? The ice acts like some source that's taking away energy, right? It's cooling the water. So this water is being lowered in temperature, and therefore the energy of the water is decreasing. So the energy of the water is decreasing, therefore the change in energy is decreasing or less than 0, and the change in energy for the ice is greater than 0 because it's being warmed up by the water. Okay. So this is another example. We won't have time for this. Just do this at home when you can, but we'll go into the next points. Conduction. So these are different ways in which energy is transferred. So conduction is really simple. It's the process by which energy is transferred through physical contact. So when I'm touching some surface, energy is being transferred from that surface to my hand and vice versa. Okay. Conduction is really simple. The really complicated ones, however, is convection and radiation. They're not that complicated, but more complicated than conduction. So the way convection works is that when you have a hot object or hot liquid and a cold liquid on top of each other, since the hot liquid is less dense than the colder liquid, the hot liquid will rise up right to the top, okay? And as it rises up, this cold liquid will drop down to the bottom, okay? And what this is going to create is the momentum of this hot liquid rising up will keep it in the same motion. So what's going to happen is that as this hot liquid rises up, this cold liquid will rise down, and it will push this hot liquid So there's going to be some remaining hot liquid at the bottom. It's going to push this remaining hot liquid and it's going to create a cycle, right? And this cycle is called convection. And it doesn't just apply to liquids, it also applies to gases. So if you have a gas, what's going to happen is the same thing, right? It's going to flow up and down in the cycle. It can't really happen in a solid because all the particles are closer to one another. So it's hard to separate them. But for liquids and gases, they're more free to move. That's why convection can occur in liquids and gases, okay? So that's that. Radiation, on the other hand, is heat transferred from a direct electromagnetic source. For example, the sun, fire, the microwave, anything, right? So electromagnetic radiation being some external source, right? Which has some energy. That's radiation, okay? Thermal conductivity. So what this states is that the power, so this is given as power, energy over time is given by the thermal conductivity of the material multiplied the surface area. So for example, if I have some surface, right? Energy is going to be transferred through this surface. So if I have some hot object on this side, another object on this side, slowly but surely, energy will be transferred through this object, okay? And this formula describes the rate at which this energy will be transferred through that surface, all right? So we'll apply this into this question. So we write down our formula at the top. So Q over T equals Ka change in T over D, okay? And we'll apply. So calculate the rate of energy transfer by conduction through a house wall, which is 1 meter squared. So the surface area of this house wall is 1 meter squared. So A equals 1 meter squared. And this wood is 10 centimeters thick. Okay, so since we're dealing with meters, we're going to convert the centimeters to a meter. Okay, so 10 centimeters is 0.1 meter. Assume the inside temperature in this house is 21 degrees. All right, so this house is 21 degrees Celsius, and the outside temperature is 10 degrees Celsius. Okay, the thermal conductivity of wood is at 0.15 watts per meter per Kelvin. But really, we're just going to write K equals 0.15. But since the unit is really complicated, we'll just leave it as that. And what we have to do is heat is being transferred from here, from this out inside the house, right, to outside the house, right? So they want to reach equilibrium. So heat is being transferred from inside the house to outside the house, since it's getting colder and colder since the outside temperature is colder. So what's happening is that Q over T is equal to 0.5. So we're just plugging your values in, times 1 times the change in temperature. So the change in temperature being from the inside of the house to the outside of the house, which is 11, 21 minus 10, over 0.1. Okay. So if you plug all this into your calculator, you should get 16.5. Okay, and this should be watts. So the energy transfer is 16.5 watts. All right, we'll go into latent heat. So basically, latent heat is describing the amount of energy absorbed or released during a state change. So a state change being when an object is going from a solid to a liquid, or a liquid to a gas, or vice versa when it's going backwards. And if you notice in the graph, the temperature is staying constant as heat is being added. This is because as temperature is being added to the system, so normally, actually we'll go to a different example. So normally when heat is being added to the system, the average kinetic energy of the system is increasing. Therefore, the temperature is increasing, right? But as this temperature, or as this object is transferring to an actual liquid, all that energy, all this extra energy being supplied in this section is being used up to actually break the bonds of the particles. So it's actually breaking the bonds of the particles to make it into a liquid. So instead of the energy going towards increasing the temperature, it's going towards breaking the bonds of the actual material itself. That's why we don't see the temperature increasing as heat is being added when the object or the material is being melted or vaporized in this case, okay? So The formula for latent heat is given by Q equals ml. So the amount of energy equals mass times the latent heat. Okay. So this is a pretty simple example. How much energy must be removed from 2.5 liters of water at 0 degrees to produce a block of ice at 0 degrees? So what this means is that we're going backwards, right? We're going from some ice over here, and we're going to a liquid. And what we're trying to find is amount of energy. So we're trying to find this much, what I highlighted here, that much energy, okay? So if you use our formula, Q equals ml, we know that the mass is 2.5 kilos, since liters is essentially the same as kilograms, times 3.55. Yeah, and latent heat is a constant. So they'll always give it to you in the question. You will never be asked to know the latent heat. And what this will give us is 0.55 is 833.88 joules, right? So 833 joules must be needed or must be removed from this ice to actually convert it into a liquid, right? So this amount of energy, this straight line energy, would be 833.88 joules. Okay. Okay. For all of that, we're going to move on to electricity and magnetism, right? So charges. So charges are basically something that make up the universe, and charges can be distinguished into 3 different types: a neutron, a proton, and an electron. All right. So these charges, they each make up an atom. So an atom consists of a nucleus and some electrons. In this nucleus, what we have are neutrons and protons, right? So we have protons and neutrons, okay? Neutrons. And surrounding this nucleus will be electrons. So if you draw a circle or some shell, surrounding this nucleus will be electrons, all right? And the amount of electrons surrounding this atom, if the atom is natural, if nothing was done to this atom, then the amount of electrons will be the same as the number of protons, okay? And since the amount of electrons is the same as the amount of protons, and the protons and electrons have the same amount of charge, the atom itself will have a neutral charge, okay? So the atom itself won't be charged. It's only when we start removing electrons or adding electrons will the atom gain a certain type of charge, okay? So charges here, this is to recap. So neutrally charged, so neutrons have no charge, positively charged. So if an atom loses electrons, that means it has more protons than electrons, right? If an atom has more protons than electrons, then it's going to have an overall net positive charge. That's why we say positive charge for atoms that lose electrons. It's the opposite for negative charge. For negatively charged, the atom must have gained more electrons to be negatively charged, since there has to be a net negative charge, okay? And obviously neutrally charged means there's no change in electrons, what we discussed earlier. Okay, so these are 3 different ways to describe how charges can change. So friction being when 2 objects are in contact with one another and rubbing occurs. So if you rub 2 objects with one another, electrons will transfer from one object to the other object and vice versa. Conduction is when a charged object touches a neutrally charged object or something of opposite charge and transfers some electrons to the other object. And induction is the same thing, except this time it doesn't touch the object. So conduction would be two spheres. So imagine you have 2 metal spheres that touch each other and transfer energy. And for induction, it doesn't have to touch. It just has to be near the other object. Okay, so that's the difference between conduction, induction, and friction. Okay, so Coulomb is a unit for describing charge. And the charge of 1 proton is positive 1.602 times 10 to the power negative 90, and charge of an electron is obviously just a negative version of that. And Q is the symbol to represent a Coulomb, okay? So when we have a charged object like an electron or proton, they will have some sort of electric field. And what an electric field is, it's just a field or like a type of space where any charged object experiences some sort of force. Okay, that's what a field is. And the special thing about a field is that it's a vector quantity. So this field, in this example here, in this proton example, the lines coming out of it is the direction in which this field is. And the size of this field would be this, or basically the charge of the proton, 1.602. But just remember, the field is a vector quantity. And we basically model a field using lines. So for a proton, the field lines go outside, so they're going out of the proton. And for a negatively charged object or an electron, they're going towards the actual electron. Okay. Parallel plates. So this was having like protons and electrons was one way of having electric fields. Another way to actually create an electric field is create or supply electricity to two plates. So when we supply electricity to two metal plates, what happens is that the one plate becomes positively charged and the other plate becomes negatively charged. And since they are opposite charges, so one's positive and one's negative, they're going to create a field that is uniform and that attracts each other. Okay, so the field lines will look something like this. They go from the positive to the negative, positive to negative, positive to negative. And one important thing with this field is that the electric field strength, the strength of this field, no matter where you are, is constant. So that's what it means by uniform. No matter where you are within this boundary of the field, it's constant. If you're here, it's the same. If you're here, it's the same. If you're here, it's the same. If right in the corner, it's the same, as long as you're inside the field. As soon as you go outside the field, at this point, at this point, at this point, the field will diminish in strength. Okay, so just remember that the field at any point in the plates will be uniform or constant. Okay, so the force on the charge. So if a charge is inside an electric field like this, so if you have an electron in here, the force experienced by that electron, this electron over here, E, will be described by this formula. F equals QE. This is a really simple formula to remember, and it's also in your reference sheet. And we'll look into some examples of this where we use it later. But just remember, the force on an actual proton or electron or any charge for that matter is described by this formula. F equals QE. Okay? And the actual electric field strength, so the strength that these two plates actually provide, is given by this formula. E equals VD. So V being the voltage, how much energy is being supplied to those plates, and the distance being the distance those plates are supplied. And knowing those two quantities, you can find the electric field strength. All right. So we'll do example 2. So two parallel plates, 6.0 times 10 to the power negative 2 meters long, are separated by 2.5 times 10 to the power negative 2 meters and have potential difference of 850 volts. So let's just write all our information down. So we know that the volts equals 850 volts. Okay, so the energy. And we know that these plates are separated by 2.5 times 10 to the power negative 2 meters. So don't get confused with this value here, right? The D in the formula represents the distance between the two plates, not the length of the two plates. It doesn't matter how long the plates are, as long as you know the distance between the plates. So we're using this value here. The 6.0 times 10 to the power negative 2 meters is a red herring. It's trying to throw you off. Yep. So just trying to understand the question and apply your information from that. So this is 2.5 times 10 to the power negative 2 meters. What is the magnitude of the electric field at point P? So remember, previously we discussed that the electric field strength at any point in the field is constant. So no matter where you are, if you're at point P, it's always going to be the same. So we can just directly apply this formula of E equals V over D. All right. And if we apply this formula, E equals 850 over 2.5 times 10 to the power negative 2. Solve this into your formula. You get 3,400 volts per meter. Volts per meter. Another unit you might see instead of volts per meter is newtons per coulomb. Whatever you prefer, each of them will suffice. But I just use volts per meter. That's my personal preference. It's just a matter of preference. So the answer will be 34,000 volts per meter. So that's an electric field strength at any point. Doesn't matter whether it's at point P or over here. Okay. So work done. So the work done basically describes the amount of energy needed to move a certain charge in a field through some potential difference. So if you move a charge from this point here to any point here, there's going to be some work done, right? Because it's increasing its energy. It needs to go against the field or go attract the field. So if this was, say, a positive or negative charge, an electron, right? If it's going towards this negative plate, it needs to do work, since the negative plate is going to be repelling the electron. So that's what work is describing. And work is only done when the actual particle moves perpendicular to the plates. So if the particle moves parallel, so that if you have an electron like this and it moves parallel like that, there's no work being done, right? There's no work being done because it's not actually changing its voltage. There's no potential difference between the distance it travels. The only way you can have a change in potential is when you travel perpendicularly to the plates, okay? So that's a really important point, and students mess that up a lot of times. So just remember that the potential, that the work being done only occurs when the particle moves perpendicularly to the plate, okay? So calculating work, the way that work is actually calculated is by this formula. Work equals QED, right? Where D is the distance the particle travels from one plate to the other plate. So if you're given a question, say like this, calculate the work of an electron to go from one plate to the other plate, what you would do is just sub in the distance between the two plates, right? But if you're not asked between the two plates, if you're asked calculate the work being done for an electron to move from maybe 1 meter out from the plate to another meter out from the plate, what you would sub in is this distance here, the distance the electron travels. So remember, the D is not always the distance between the plates. It's the distance that the particle actually travels across the plates, okay? That's a really important point, okay? So calculating work, this way to calculate work, we'll go through this example. So a student sets up parallel plate arrangement so that one plate is at a potential of 12 volts and the other plate is positioned at 0.5 meters away. So we'll always draw a diagram. Always helps to draw a diagram. So one plate is 0.5 meters away. 5 meters. All right. And it says that the voltage or the potential difference, so the potential difference meaning the voltage difference between one plate to the other is 12 volts, okay? So the voltage is 12 volts. Calculate the work done to move a proton from the earth plate a distance of 10 centimeters towards a negative plate. So if this is our negative plate, and this is our earth plate or positive plate, we're trying to find the work being done to move this proton a distance of 10 centimeters. And 10 centimeters is just 0.1 meters. Okay, so what we need for this question is to find the electric field strength, right? Because if we look at the formula for work, it's work equals QED. We need an E, right? And that E just represents the total electric field strength of this field, of these two plates. So to find this, we're just gonna use our old formula. E equals V over D. All right, so we need two formulas for this question. So E equals V over D. We know that the voltage is 12. So we sub in 12 there. And we know that the distance between the two plates is 0.5. So 12 over 0.5 will just give us 24 newtons or volts per meter. Okay, 24 volts per meter. Now, what we can do is sub it into our work formula. So we just write this in the corner, E equals 24 volts per meter. We rub that out just to get some more space. Okay, and we'll just simply sub in all our information. So we know that Q given in the question is 1.602 times 10 to the power of negative 19, but that's also given on our reference sheet. So we just write that down here. Times E is 24 times our distance the proton actually moves. So remember that distance is the distance the proton moves, is 0.1. And if you sub that all into your calculator, 1.602 times 10 to the power of negative 19 times 24 times 0.1 is 3.84 times 10 to the power of negative 19 joules. Okay, the units for work is joules. So that the work done is 3.84 times 10 to the power of negative 19 joules. And the last part of the question says, in your answer, identify what does the work and what the work is being done on. Okay, so this proton is of positive charge. Okay, it's of positive charge and it's being moved towards the negative plate. Now, negative charges and positive charges attract each other, right? So essentially what's happening is that this plate, this negatively charged plate, this highlighted plate over here, is attracting this proton. So what's doing the work is that this field or this plate is doing the work in attracting the proton towards it. So what you would write in your answer is what does the work is the electric field or the plates, the two setup plates, does work on the proton. If the proton was going towards the positive plate, so if this was positive instead, if these were positive, since the plates repel the proton, but the proton is moving against that repulsion, the proton is therefore doing work against the field, okay? So for this answer, it would be, since the top plate is negative, it would be the field does work on the proton, okay? Coulomb's law. So Coulomb's law just describes the force between two charges separated at some distance. So if you have two charges like this, they'll obviously have some repulsion or attraction force, and that force is described by this formula. And this value here is just a constant. It just describes how easy it is to move a charge or inhibit an electric field or move a charge in an electric field. That's all that constant describes. You don't really need to know what it means. Just know that it's a constant and the value of it is given in your reference sheet. So the value of this epsilon delta or this permittivity of free space is given in your reference sheet, okay? So we won't have time to go through that one. So do this in your own time. Do this example in your own time because we won't have time to go through it. And we'll just move on to electric circuits. So electric circuits basically is the flow of electricity through a closed loop. And what's really important here is that it has to be a closed loop. It has to be a closed loop. If an electric circuit is broken, say if this is our electric circuit, obviously no electrons can jump across this gap here. So no current or no electricity would flow through this circuit. So an electric circuit will cause charges to flow only when it's a closed loop because electrons can't jump across this bridge over here, okay? And the flow of charges is called electric current. So this is another important point. So flow of electrons or any charge is called electron current. It's called current. And the direction in which we actually analyze these circuits is called conventional current. So electron current is when it's the flow of electrons. So if we have a battery like this, we know that in a battery, the smaller end, this end represents the negative terminal. So if that's the negative terminal, then this must be the positive terminal. So electron current is the flow of electrons. So if electrons are flowing, that would mean electrons are flowing from this negative terminal all the way to the positive terminal. But when we're analyzing these questions, what we do is we consider or we assume that the electrons are in fact traveling in the opposite direction, in positive direction. We just do it that way since it's a convention, but just know in reality, electrons are actually flowing in the opposite direction. It doesn't change our calculations. It's just a way to actually perform or represent our information, okay? So we'll go into electron circuits. Yep, electron flow. So current, so this is what we described earlier. Current is just defined as the flow of charge. So how many charges are passing through a certain point in the conductor material at a certain amount of time. That's what charge is describing. And what current is describing. And current can only form when there's no break in the circuit. So the circuit has to be fully formed for current to actually flow, or for electrons to actually flow. Okay. And the formula for current is given by the amount of charge that passes through a certain points in the material at some certain amount of time. So I equals Q over T. So why it says N times Q is that if you have multiple electrons, the net charge of those electrons will be one electron, the charge of one electron plus the charge of another electron plus the charge of another electron, right? So the total charge will be N times Q, right? So the total current would be NQ over T. But if you're just given one electron, the current of that electron would be given by Q over T, okay? And the units for current is given in amps, okay? Amps. Okay, potential difference is the same thing as we described earlier. It's amount of electric energy some circuit has. So if you have a battery, the potential difference is the amount of energy supplied by that battery. And why it's a difference is that this potential energy throughout the entire circuit is lost. So as you flow through this circuit like this, what's happening is that energy is being lost. So as you're flowing, energy is being lost. So maybe at the start, this battery had 8 volts of energy. And as these electrons flow through, they're flowing through like this, they're slowly losing energy, such that at this point, when they reach the other end, it's 0 volts of energy. So the potential difference of this battery would be 8 volts minus 0 volts, okay? Which will just give us 8 volts, okay? So remember, the potential difference is the change in energy or the change in volts of the actual elements in the circuit, or how much energy the electrons or current loses in the circuit, okay? Power is given by how fast or how much the rate of change of energy, E over T. And for a circuit, if you want to calculate the amount of energy this circuit provides, it's given by power equal to VI. This is another important formula. So this just relates the amount of voltage and current. So if you know the voltage, so this battery has 10 volts of energy and the current flowing through that circuit is 10 amps, then the power would be 100 watts. So that's how much energy or rate of change of energy that circuit is producing, okay? So this is a really simple example. All you do, power equals VI, is multiply 230 with your amps. So 230 multiplied by 4, and that will give us 230 multiplied by 4, 920 watts, okay? So really simple example. So resistance, so we look through current and voltage. Now we're going to look at resistance. So resistance is just a measure of how much the wire actually impedes the flow of electrons. So how hard is it for the current to actually flow through the material? That's all that resistance describes. So you can imagine as if we zoom into the wire like this, imagine we zoom into this wire, the electrons are flowing through this wire. So depending on the thickness of this wire, as these electrons flow through this wire, they're going to bump into the edges of the wire at some points. And at some points, they're going to lose energy. And resistance will describe how much the flow of electrons actually is decreasing. So how much energy they're actually losing. So resistance is all it's describing is how difficult is it for these electrons to actually flow through this wire, okay? And Ohm's law, all it says is it gives us a relationship between the voltage, the current, and the resistance, all right? So if the wire isn't changing in its temperature, so we're just assuming that the temperature of the wire doesn't change, then the relationship between voltage is given by V equals IR. And this is probably the most important part in the circuits part, in the circuits module, is V equals IR. You're going to be using this everywhere, okay? And we'll apply this, okay? So if you apply it, so this is a pretty simple example. We won't waste time on this one. We'll look at an application of Ohm's law a little bit later. But for now, we'll keep on chugging through. So series circuits are basically circuits with one continuous loop. So an example of a series circuit would simply be this. If you have some sort of lamp, this is our lamp, and this is our battery. This would be a series circuit, since it's one continuous loop. These are really simple circuits to construct because all you need is one wire, battery, and a lamp. But the problem with these circuits is that if there's a break in the circuit, say if the wire is faulty and there's a break like that, no current can actually flow anymore. And therefore, there won't be, this light bulb won't be able to turn on. So that's a disadvantage of a series circuit. So an advantage of the series circuit would essentially be the how easy it is to construct a series circuit, and a disadvantage would be its resist, or like how hard or what's it called? It will cause a break, and if it causes a break, then obviously we'll know the series circuit is not as well as some other circuit. So we're going to look into another circuit right now, conservation of charge. So what this states is that no circuit or no energy is or no charge is actually lost in a circuit. So if you have a charge flowing through or current flowing through this wire, no charge will be lost throughout this wire. The reason for that is since the wire is encased in itself, no electrons can actually go out from the charge. So what's happening is that the electrons are just bumping into one another, bumping into the surface, and they're just losing energy. So the conservation of charge says in a circuit, no electrons are lost since the circuit itself is enclosed. So no electrons can actually escape. Only energy is lost from the current. So this is an important point, and we'll see an application of this a little bit later. Okay, Kirchhoff's voltage law. So what this states is what I said earlier, is that if you have a circuit, so we'll go back to the original circuit, the amount of energy gained by this circuit, so this is 8 volts, so the amount of energy gained by the electrons in this circuit, so the flowing, will always end up at 0. So the amount of energy gained is equal to the amount of energy lost by the electron. So this is another application of the law of conservation of energy. So it states that the electrons must end up at a point of zero joules of energy once it reaches the end of the battery. So if this is our electron over here, they're traveling throughout the wire. As they reach this light bulb, they'll have 8 volts of energy. And since this light bulb consumes some amount of energy, when it exits, it's going to have 4 volts of energy, right? So this light bulb then consumed 8 minus 4 volts of energy. So then as these electrons continue to travel on, they will have 4 volts of energy. And as they're traveling, since the wire has some thickness to it, the resistance will cause them to lose energy over time. And as they lose energy over the time, once they reach the end, they're going to have 0 volts of energy. So as it circulates through, it's going to have 0 volts of energy. So that's what Kirchhoff's voltage law is saying, that the total voltage drop around a closed circuit must equal the total voltage gained in the circuit. So essentially, it's just the second dot point here. All right. Yeah, so this is what it's saying. So as it's traveling, it's going to have some total energy over here. So some V is going in, and then it loses some energy. So the voltage drop at this point will be V2. So this voltage at this point will be less than V, and it's chugging on until it reaches this point over here. And then it's going to lose some amount of voltage until it reaches this point. And so the potential difference from this outside point to this other point will be V1 until all the way it reaches at this point, at which the voltage will be 0. Okay, so that's called Kirchhoff's voltage law. Equivalent resistance. So if we have a series circuit, the total resistance of that series circuit will be given by this formula. It's pretty intuitive. All you do is add up the individual resistances of the resistors in the circuit. So if you have multiple resistors like this, multiple resistors, the total resistance will be this resistance R1 plus this resistance R2. And that will just describe the, so if you have two resistors like that, that's the same thing as saying you have a one big resistor with that same amount of resistance. So then you can redraw the circuit as R1 plus R2. That will be your new circuit. So this equivalent resistance formula just gives us a way of redrawing our circuit diagrams, okay? So we'll go through this example here. Use the equivalent series resistance to calculate the current flowing through in this series circuit. Okay, so when applying Ohm's law, what we want is this R to be the total resistance of the circuit. So instead of using this diagram, we can kind of redraw it, right? So the way we would redraw it is we'd calculate the total resistance. So the total resistance would be 100 plus 690 plus 330. And this would give us 100 plus 690 plus 330. This would give us 1120 ohms, okay? And essentially what this means is that we have a circuit with one big resistor of that many ohms, okay? So I'm just redrawing this circuit to make it easier. You don't have to do it for this simple example, but just to show you guys, I'm just making an easy example, okay? So this would be 1120 ohms, correct? And we know that this voltage is 12 volts. So now that we have a simple circuit of one resistor and one voltage, we can apply Ohm's law. So applying Ohm's law, V equals 12, I equals unknown. We're trying to find what the current flowing through this circuit is. And we know that the resistance is 1120 ohms. So the current would be 12 divided by that. And that would give us 0.01 amps, all right? So for resistors in parallel, it's a bit different in the sense that it's described like this. So you have two different branches. One branch branches off into this direction, another branch branches off into this direction. And the benefit of parallel circuits is that if there's a break in one of the branches, it won't affect the other branch since the current can still flow. So if there's a break in this circuit here, the current can still flow in this direction, right? Since there's a closed loop. So that's an advantage of resistors in parallel. And the way to calculate the resistance for resistors in parallel is a bit complicated to the other example, since you're adding not to the same branch, you're adding to a different branch. And we'll look into that later. Okay. Kirchhoff's current law, what this states is that it's pretty intuitive, but we'll go through it. What this states is that this circuit here, this main circuit where the battery is supplied, has some current I. And when this circuit branches off, this current I will be split into different components. So we split into an I1 and an I2, okay? So this dot will be your junction, okay? So then these two separate currents will flow through their individual branches until they reach another junction, at which point they will add up together. And they will add up together such that it forms the original current of I. So then I would equal our I1 plus our I2. Okay, and that will tell us how to find the current in each of the branches. And that's just Kirchhoff's current law. It's a pretty simple law, and you can apply it for multiple branches. So if you had another branch, it would just be I1 plus I2 plus I3 all the way up to n branches, okay? So this is what I was talking about earlier, the equivalent resistance. So the total resistance in a series circuit is given by this. So 1 over RT is given by 1 over R1. So 1 over R1 is the this R1 is the resistance in one branch, okay? So if this branch was our branch 1, the resistance, the total resistance in this branch would be our R1. So it's not just considering one resistor. So if we had one resistor, it's considering the total resistance. So if we had multiple resistors, so if we had 2 resistors, 3 resistors, the R1 would be the total resistance of one branch. And that's how you'd calculate this formula. You would do it for successive branches. So for R2, it would be the same, 1 over R2, all the way up to n branches. And then you would reciprocate that again to get your RT. And the RT would just be 1 over all this, 1 over R1 plus 1 over R2 dot, dot, dot. All right. So this is a pretty simple example. We won't go through that one. Actually, can you guys try example 2? I'll go through example 1 since we're running really short on time. So what we do in this one, we calculate the total resistance. Resistance RT is equal to 1 over 200 plus 1 over 100. So the total resistance would be 1 over 200 plus 1 over 100. Okay, would be 200 over 3 ohms. All right, so that would be the total resistance. Oh, all right. And one thing I forgot to mention is that in parallel circuits, the voltage across branches will stay the same. So even though the current changes, so the current is split, the voltage will stay the same. So this branch will have 12 volts and this branch will have 12 volts. Okay, so the current will split in branches, but the voltage will stay the same. Okay, so that's a really important fact to know, and it will help us with this question. And it looks like I don't even need to calculate the total resistance, since it's asking us to find the current flowing through. Oh no, so I do need to calculate the parallel resistance. So then to calculate the current flowing through resistor 2, so I1 would be V over R. The voltage is 12, since the voltage across the branches is the same, over 200, and that would give us 12 over 200 as 0.06 amps. And it's a similar process for I2. I'll let you guys do that one since we're running short on time. Okay, magnetism. So magnetism is basically a phenomenon which two magnets can, or a field causes some sort of attraction between a material. And these materials can either attract or repel. Okay, and every material will have some sort of magnitude of magnetism. They can be smaller or larger depending on that certain material. Okay, some basics on magnets is that north repels north. So it's similar to charges, how the like charges repel and unlike charges attract. It's a similar for magnetism in that like magnets repel and unlike magnets attract. Okay, direction of field. So the way we actually draw magnetic field lines is that we go from north to south. Okay, so magnetic field lines always go out from the north and then into the south. So if you ever get confused, just think of the charge case. So in charge case, it was a positive as going out, and the positive charge would be analogous to the north magnet, and the negative charge would be analogous to the south magnet. So this would be the same as the north magnet, and a negative charge would have the same field lines as the south magnet. Okay, so field lines go out from the north and go into the south. Okay, magnetization. So how something becomes magnetized is if you have a ferromagnetic material, so something that isn't permanently a magnet, a ferromagnetic material will have some magnetic domains. Magnetic domains being mini magnets. Think of it as mini magnets inside the actual ferromagnetic material. And the way this ferromagnetic material becomes magnetized is if you bring another magnet in the presence of that ferromagnetic material, all these mini magnets or these domains inside this ferromagnetic material will align such that they become uniform. Like in this case over here, they become uniform. And this causes the ferromagnetic material to be magnetized in itself. Okay, so these ferromagnetic materials only become magnetized when in the presence of another magnet. They're not naturally magnetic. Okay, so that's ferromagnetic materials. We'll go through magnetic fields around current carrying wires. So when a current flows through a wire, it's going to have some sort of magnetic field surrounding it. It's just a natural phenomenon that happens. And the way you describe this magnetic field is through the right-hand rule. So your thumb will represent the direction of the currents, and whichever direction it goes, your other fingers will curl around. And the way they curl around will be the direction of that magnetic field. Okay. So if you draw this in 3D, so if you point in the direction of the wire, it's going up. So my fingers are going into the page, right? So they're driving inside the page and they're going outside the page, right? So each point where it's an X is the points where the magnetic field is going into the page, and points where it's a dot are the points where the magnetic field is going outside the page. Okay. So when you have two wires, they can either attract or repel. And the way you determine it is that if the currents in either wire are traveling in both directions, then the wires will attract. If they're traveling in opposite directions, those wires will repel. Okay. And Ampere's law describes the magnetic field at a certain point. So if you have a wire of some current I, this B states that if you at any point, so at this point R from the wire, the magnetic field is described by this formula. So if this would be R, you can find it at any distance. So imagine that this is 2R. So that's what Ampere's law states. And obviously the further out you go, the magnetic field strength would diminish over the distance. Okay, so that's what this formula describes. I'll let you guys do this example at home because we're running out of time. And we'll go through the solenoids. So magnetic field around the solenoid. So if you have multiple wires and you form them in a shape such that it looks like this, so with loops, multiple loops, what's going to happen is that magnetic field strength will amplify since there's more and more loops. Okay, and it will look something like this. The way you determine the direction of this field would be you follow the current. The current is going up, going this way, it's going down. So using the right-hand rule, the current is flowing this way. So the current is curling into the page like that. So then the magnetic field strength pointed by your thumb would be outwards. So since your thumb is pointing this way, this would be your north and this would be your south, right? So the reason a magnetic field is formed like this is because each of those currents are amplifying onto each other, forming a magnet like this, okay? And Ampere's law, another form of Ampere's law, states that the magnetic field strength of this solenoid is given by this formula. Mu naught, and the permeability of free space multiplied by the number of turns, multiplied by current flowing through this wire, the current over here, multiplied the overall length of the solenoid. So this length over here, this length, that length, okay? That would be Ampere's law. Okay, so since we're all out of time, I'll have you guys do these examples that we didn't go through at home, but that should be it. If there's any questions, just post it into the chat now. Other than that, I'll let you guys, we should be done for today. And you guys can head off. Are there any questions? No questions? All right, I'll end the meeting here.
Hey, how do you get the notes?
Oh, the notes, we'll send it to you. So
And the practice paper?
yeah, we'll all send that to you. So we'll send it to you after this.
All right. Thank you.
No worries. So if there's no other questions, I'll end the meeting here and thank you everyone for coming. And good luck with your prelims.
What about the recording? Is it possible for you to get?
Yeah, so
that
we'll
too?
send the recording also.
Okay.
Yeah, no worries. All right, see you everyone.